I think, reviewed expectation. And was that clear? Do you all know how to define the mathematician's definition of expectation? No. So one way to define expectation is to say, well, if it's a discrete random variable, take probability 101, and what the definition of an expectation of discrete random variable is, and then just say, well, I can approximate any random variable by discrete random variables. That's what Neil briefly surveyed last Tuesday, and you should have learned that if you took the part 1 course. You should have actually seen that. All right, but you could also just skip that and make another definition. So it turns out that if you look at, check this out. What's the integral from 0 to infinity? Let's just make a restriction. Let's assume that we have a random variable that's non-negative. I can always write it, for any random variable, I can write it as its positive part minus its negative part. So we can just look at the positive part. And then most of you have seen this before, this wonderful trick. You look at this integral, but some of you haven't, okay? So just be patient. So a probability is also an expectation. Okay, so you'll see me use this a lot, this indicator function notation. It's really helpful. So when I write indicator function, it's just 1 or 0 depending on whether the event holds or not. So I'm looking at this event that the random variable exceeds the value r, and it just takes on 2 values. So it's an example of a simple random variable. It just takes on 2 values. And so the expectation of that is just, the probability is just the expectation of that indicator function. It's the same thing. It's the definition. All right, and then you can exchange expectation integrals. You can do that for non-negative random variables. So again, take an analysis course. It's called Fubini's theorem. And don't worry, I'm not expecting to be mathematicians. I'm just telling you why I can justify this swapping of expectations and integrals. They're both integrals in some sense, and you can swap integrals when you have a non-negative random variable. And then this is sort of fun. I mean, this is a really boring integral. I mean, let's map it out. Let's map. I've got the r-axis here, and I've got the indicator function that x of omega is greater than r on the y-axis, right? And say r is 12. I don't know. R is some positive number, oh yeah, that's right. R naught. Let's take. I mean, I shouldn't. Sorry. Greater than r. No, I got myself confused, but it was fine. What's this thing here? What did I mark here? What's important here? So when r is 0, it's likely that this fails. And then suddenly this is going to be 1. And I almost made a mistake when I marked this axis. What's that? So I'm going along, and suddenly this is 1. For what value of r? Yeah. Oh no, r is big. It's the other way around. When do you look confused? Okay, so let's try this again. If R is really, really big, this is impossible. X omega is 12, sorry, not R. All right, so I flip this around. So this happens in this. And what's that place? I screwed up before. Come on, somebody scream it out. No, right there's a break point. So I'm plotting, this axis was R. So R is really small, yes, we get a 1. R is enormous, it's no longer true. When R equals X omega, something changes. Okay, all right. And so what's the integral of this funny function of R? It's the base times the height, so it's X. So all right, so we could make that the definition if you like, I mean, I could put a definition sign there and just say that's the definition. So I could say, for a positive random variable, I define the expectation to be the integral of this probability. And that's that. So you could forget the abstract nonsense. Just make that the definition of the expectation of a random variable. Why not? Okay. All right. So you could do the approximation by simple functions. Well, that's really what this is. We're really, this integral, this integral here is expressing X. And if you replace the integral approximate the integral by a sum, you'd be approximating X by simple functions. So really this is just a clever way of saying what was already said. Right? And so what's another way of expressing this in terms of that over there? F of C is a probability that X is less than or equal to C. There we look at the probability that X is greater than R. So, yeah. All right, first
why is it term off? Why does it go back to 0?
Oh, because R gets big. If R is bigger than X, it's 0.
What's the marking on that?
X omega. So if when R equals X omega, something changes.
Right.
And R is bigger than X omega, it becomes 0.
It becomes 0?
Yeah, I mean, look at the definition. It's 1 if R is less than X omega, otherwise it's 0. So the break point is when R equals...
Once you pass R, it should always be...
no, once you pass X omega.
Yeah.
No, there's a function of R. See, that's where I got myself confused and I made you confused. So I'm fixing omega and I'm graphing this as a function of R. And if R is 0 and X omega is positive, this is 1. And as R increases, it's still 1. And it's just only when R is equal to X omega, wham, you jump down. And you jump down in it's open and closed. Is that right? At this point, when R is equal to X omega, then this is no longer an inequality. So it's actually like that. Yeah. But anyway, the probability that X is bigger than R is 1 minus the probability that X is less than or equal to R, just using the union formula. And so it's equal to 1 minus F of R. Okay, so there you have it. So again, you could just take that as a definition. It's just an ugly definition to work with. That's the thing. It's not. I think that's much more useful for calculations than for any theory. All right, but it does come up. I've used this. Well, I'll give you an example where I've used this. As you've seen, I sometimes get frustrated with calculus, even boring calculus. And more than once, I've had to double check what the mean or variance of an exponential random variable is. and it's much easier to work with that definition than the primary definition. So take an example. So x is exponential lambda. That means it has a density. Okay, so it's a review. A exponential random variable has a density of that form. Okay, so that thing integrates to 1, a bit of easy calculus. And if you ask for the mean of x, that's equal to the integral from 0 to infinity of r f sub x of r dr. That's the definition that would be given in a baby probability course. And it's a bad definition, because you say, if I have a density, here's a definition. If it's discrete, here's a definition. If it's mixed, what do I mean by mixed? So, that's why this is for calculation, not for theory. But then I get annoyed when I see r e to the minus lambda r, and I know I have to use integration by parts. I'm like, oh, Jesus, forget it. So I just do this instead. I just say it's the integral from 0 to infinity of that. And the thing is, I'm cheating here because I already know that f of r is 1 minus e to the minus lambda r. That's not really cheating, because the thing is that ddr of f of r is equal to little f x of r. That's how I know that, So I'm using a little bit of calculus on the side. So the derivative of the CDF is the density if a density exists. And just check the derivative of that is equal to the density. Right? And then everything, and that's not a minus sign, it's a scribble. And then you just get the integral of e to the minus lambda r. So this is just a diabolical way of doing that integration by parts. So we all know that if I had the lambda there, I would get 1. So without the lambda, I get 1 over lambda. Yeah. All right. Yeah. Now, but this doesn't always work. I mean, suppose I wanted the second moment. All right. Well, we can know it's equal to the integral of x squared f sub x of, r squared. And we could try to just brute force, say, wow, this was a miracle. I avoided integration by parts. Let's try to do this. Well, you could say let y be equal to x squared, and then we could try to come up with f sub y of r, which is a probability that y is less than or equal to r, which is the probability that x squared is less than or equal to r. So we could try to find the cumulative distribution function for y, and then perform this trick. And that's no big deal because x is not negative. I can invert. So if x took on positive and negative values, taking the square root, I'd have to look at when x is negative and positive. But here it's just equal to the probability that x is less than or equal to square root of r. And you could say, yes, I did it. That's 1 minus e to the minus lambda times the square root of r, and I'd be in more trouble than I could ever believe. And I just couldn't do it. So now I'm stuck. It's really funny. I mean, just completely hopeless-looking integral. And yet it's trivial. You can do integration by parts twice here. It's trivial. You try to integrate that, you just have to stick it into MATLAB or Mathematica. All right. Cool. All right. I do not want to end on anything that's not. All right. So it's 4:30. When are we supposed to quit?
4:55.
4:55. So let's do it. One last thing that's fun, and then we'll stop. So we can define the mean of a random variable in this way. through integrating the, what's it called again? The complementary CDF, that's what this is called. So, we'll do real MCMC maybe later in the course. But like this is the dream of MCMC. I have some random variable with some crazy distribution, and I'd like to draw samples. You know, and you know, how can I generate, given a CDF, how can I generate random variables with that CDF? So in MATLAB, you can generate a random variable that's uniform in 0, 1. But if you gave me some crazy random variable, you know, I just came up with it. You know, I've got a CDF which is just our density. Based on my neural network, I got a density which looks like that. You know, and then I numerically integrated it, and I got a CDF, you know. And this is a capital F. And now I'd like to draw random variables from that density, you know. Now, there's a beautiful theory of doing that, which is called, you know, the Metropolis, Hasty Metropolis, or there's various algorithms into the MCMC, Markov chain Monte Carlo, for drawing random variables that approximately have the given distribution. For any distribution, it's amazing, you know, as long as you have a density. If you have a scalar case, it's easy in a way, you know, with MATLAB. So the trick is this. Define an inverse. All right, so it's just, when you've got this function with jumps and all that, you know, there could be some ambiguity at the jumps. And so you just nail things down by making this a definition. You know, this really is consistent with what you think of as an inverse. You take the graph and you flip the axes and all that. It's the inverse. And then you've done it. If you can compute this inverse, so if you can compute this guy and invert it, and again, inverting it is what? I pick up this on transparency and I flip it around and turn it upside down. I just get a curve like that. That's the inverse. So you can do it numerically. And then I can define x to be equal to f inverse of u, where u is uniform. Okay. So, and that has the right distribution, and that's trivial, you know. And why is it trivial? Because the probability that x is less than or equal to r is equal to the probability that f inverse of u is less than or equal to r. That's the definition. And this definition is carefully constructed, so this is exactly what you want it to be. Okay, so if you stare at this long enough, you'll realize that these are the same events, you know, given that definition. All right, again, I'm just not going to bother. And we know that for uniform distribution, the probability of being less than some number is just the number. F of r is between 0 and 1, right? So it's just, you know, this is equal to the probability that u is in the interval from 0 to fr, you know, and fr is less than or equal to 1. So it's just the width of the interval. So that's really awesome. You know, in one dimension, generating random variables with a given CDF, nothing. You know, in 2 dimensions, you know, then you need some crazy techniques. Yeah. All right. Cool. And that is a good time to end. So. it's really cool that I'm putting more burden on you. So I taught this course here like 3 times before, and I didn't quite understand what was taught in noise in the precursor. And after teaching it 2 years ago, I realized you guys are responsible for knowing what an expectation is. You saw it before, and you did play around with Omega FP before. And if you didn't, you just got to go and study chapter 1. I'm gonna assume you know this. I'm gonna assume everything I did today was pretty much review. And that means I can go and we can get into sort of the fun applications quicker. I mean, it used to take me 6 weeks to get into the fun applications. I think we can get through it faster. And if you're suffering too much, damn it, come to office hours. Or you've got the best teaching assisted teacher. What are you? I don't know. Co-teacher that's ever been at UF right there. So. And some great fellow students as well. So if you don't ask for help, it's you should be ashamed of yourself. Ask for help if you're confused. But it's going to be fun with your help. I mean, this course is going to evolve, and I'd love feedback on what you'd like me to cover. Like Aditya said, hey, let's try to squeeze in Gaussian processes. You know, if a whole bunch of you say yes, then I will definitely do it. And if nobody screams yes, and they say no, I want more on MCMC, then maybe we'll do that. There'll be a feedback loop in this course. All right. So on Thursday I'll see you all, and it'll only be an hour, so it'll be much easier. And maybe we'll have another room. I'll work on it tomorrow.